My name is Tzach, or Zach if you prefer it in English, and I currently work for Google Research, and the project I'm working on is called the Flood Forecasting Initiative. I'll give some examples and show some of the stuff that we're doing in future slides. Actually, let's begin with a video. Sorry. Yeah. So just to demonstrate what a flood is, I'm not sure where all the audience is from, but like I'm from Israel, and in Israel we don't have these kind of floods. We barely have these kinds of, we barely have rivers where there's actual water flowing in. And this is a video that was taken in a village in India. And we were actually there, I think, a few days after the flood actually hit the village. Unfortunately, that happened in the middle of the night. What really happened there is that they had an embankment. Embankment is something like a small dam that they build to divert the water. So it cannot really stop a flood, but it can divert the beginning of it. And what happened is that the water began to rise in previous days. And then at some night, the embankment just broke down. And the flood was immediately, the village was immediately flooded. Unfortunately, this was kind of a tragic event. Two people in the village, two villagers lost their lives. But having said that, it could have been much, much worse, because if it weren't for one of the villagers who was awake and was able to, first of all, wake everyone up and rescue a few people, because otherwise that's a matter of 15 to 30 minutes between, like, from the breach of the embankment to the place where you actually find yourself in your home fully flooded and you cannot escape. But as this event might sound dramatic, that actually happens a lot in places like India and Bangladesh. Those are places with huge rivers like the Ganges and the Brahmaputra, and that happens quite a lot. And a lot of people actually die every year from flooding. What we see in this slide is just some estimation of the number of affected people, okay? That's not casualties. That's only affected people by floods, or actually by weather-related disasters. And what you can see in this, this chart is that floods can account for something like half of the weather-related disasters in terms of affected people. We know from long-term statistics that in a median year, around 10,000 people will die from floods in those areas. And the economical damages are enormous. It's like in tens of billions of dollars. And that raised the questions of why does that happen? Why cannot we provide some reliable alert to these people, maybe a day or two before the flood actually hit their village, saying or telling them something like, okay, you are in an area that is about to be flooded in 48 hours, please evacuate or do something, or maybe save your cattle or crops. These are two of their main concerns, after themselves, of course. And just do whatever you can in these 48 hours and just run away, go to some hill or a mountain and just run away. And unfortunately, in developing country, there are no real reliable alerting systems for floods. So what we did is we started around 2.5 years ago, I believe, maybe 3, the Flood Forecasting Initiative. And our goal is to basically provide what's called scalable, high accuracy, high resolution forecasts and warnings globally, flood forecasts and warning. Okay, we currently do not deal with other disasters, although we have some research directions in that direction as well. And it's maybe important to mention, I'm not sure how familiar everybody with types of floods, but generally speaking, there are a few. So there is something that's called flash flood, which is more common in the desert, for example. If for people who are from Israel, then the Tzafit event a few years ago in the desert was something that's called a flash flood. The soil was too dry and could not absorb the mass amount of water that was pouring in. And then you get a flood event in like 10 to 15 minutes, something like that, as quick as that. And there are other types of floods, like coastal flooding, for example, from a tsunami or something like that, which are floods that we currently do not deal with. So we currently focus on what's called riverine floods. And riverine floods are floods that like caused by a river, by a large river that just overflows. This is the major flood type that actually caused most of the fatalities and damages. I want to show a quick overview of how the whole system looks like, but we will focus in this talk on the hydrologic model itself. Okay, so we have something that's called the hydrologic model. Hydrologic model basically takes into account all kind of weather inputs. It could be precipitation and temperature and soil moisture and I don't know, solar radiation and anything that we can use remote sensing to sense. And the goal of the hydrologic model is to predict what would be the river state in the future. So to give us some horizon into the future. And normally what we try to predict is the amount of water that will flow in the river in, for example, a day from today or 2 days from today or 72 hours or whatever. Then we have the hydraulic model, which is basically it's a physical fluid dynamics simulation. And given the amount of water that is going to be in the river and the DEM is the elevation map of the area, we can just run a very fine grid fluid dynamics simulation and see what areas are going to be inundated, but exactly what areas, like in terms of polygons on the map. And the hydraulic model can also give us, other than what areas are going to be flooded, also the flood level for every pixel in the map. So then we can maybe send to people who are in I don't know, maybe in the school of the village, it's going to be 50 centimeters inundation. And then maybe in another place, it will be 1 meter. So we can differentiate between those and tell them, like, send them different notifications. Once we've decided that a specific area is going to be flooded at a specific time, we trigger a push notification to those people, and we are also hooked to their search pages. So if they just use Google search and they search for floods near me or something like this, they will see something similar to what you see here. They will just get this alert. They'll be able to open it to see themselves on Google Maps, to see the exact polygon that is inundated, and some other information like critical information like 911 numbers and everything. That they can use during this event. Let's start again. I'll just have a slide or two on the warning distribution and the hydraulic model, and then we'll actually focus on the hydrologic model. So for warning distribution, we use a system called crisis response. That's not unique for floods. They are actually active for, I believe, something like 8 to 10 years. They've sent billions of alerts to individuals, and they support a lot, like many types of catastrophes and events that can happen. And we actually plug our model into crisis response, and we are one of the providers of alerts to people, and they do the delivery to the actual user, whether it's with a push notification or with the integration with the search page or any other mean like SMS or something. For the hydraulic model, I chose the image which I like the most. This one was taken on the same field trip, on the same field survey that we were around a year and a half ago. And what you see here is that we were actually going to India to a field survey to chase the floods, okay? We were opening our own maps, our own inundation maps, and we just told the driver to get us to the villages that we see that are currently inundated. Basically because we wanted to get the feeling of what does it look like when the village is flooded. And that is a fascinating topic for another talk. I could fill probably an hour with stories from this field survey. And that was kind of amazing and in some ways completely changed the way that we think about floods. But again, that's for another talk. What you can see here is, I believe that's the hand of Yossi Mateas. He's the VP lead of Google Israel. And he's holding the smartphone, one of our smartphones, with the alert, like with the Google Maps open, with the alert itself. And what you can see is that here you can see the blue dot, which is ourselves. And we were actually standing on the edge of the polygon, on the edge of the inundated polygon that we predicted. And what you can see in the image is that that's exactly where the water actually got to. So that's my favorite cherry-picked image. But I think it really shows what does it mean to get the alert to open the map. And then what you see on the map is actually what happens in the ground. I won't really mention the statistic and performance for the hydrologic model, basically because it's much better if someone from the hydraulic team will do it. But basically, it's around more than 95% recall and precision per pixel on the map. So it's pretty accurate. Like once we say that a specific area is going to be inundated, if the DEMs are correct, then that's very, very reliable. But let's get into what I find the more interesting part and the topic of this talk, which is the hydrologic model. So first,
can I ask a question?
Yeah, sure, of course.
Except for precision per pixel, first of all, hi, I'm Itamar. Except for precision per pixel, do you actually have some measure also of where there are large errors, not per pixel, but say by a borderline that is significantly farther away or closer away? I mean, I wouldn't, as a user, I think it would be less worrisome for me if in this meter there's supposed to be water versus did it miss by 1 meter or 100 meters?
Yep. So actually, maybe I will tell a story from this field survey, because I know that we have like quite a lot of time and we probably won't fill it with only this talk. And that relates to what you asked. So in one of the villages where we actually went to, the village was completely flooded. It's not something that you can't even walk in, or at least not me. So it's like knee level water. We folded our jeans and took our shoes on the shoulder, and we were just walking in the village, and with some local guy who took us in, and then we showed him like our alert, something similar to what you see here. And like we told him, okay, do you understand this alert? Can you read it? Do you understand like that you are currently in the middle of a flood, in the middle of a flooded area? And he was like, I understand that I'm the blue dot, but I don't understand why is it red all over me? I was like looking at him, looking at the floor, which you can obviously not see because I'm just standing in a huge swamp of water. And I'm like, what do you mean? Like, it's red because it's flooded. And look, we are like standing in knee level water all over the village. It's not like a particular point. And he's like, yeah, but I don't understand. It's not flooded. So why is it red on the map? And then after you talk to them, you understand that exactly like you asked, they don't really care about a flood which is like 10 centimeters or 20 centimeters. Actually, when we asked him, what do you do when the water start arriving? He just told us, I just take all the valuable things and put them in some box, and I put the box on the table so it won't get wet. And then what do you do when the water keep rising and it gets like to half a meter, maybe a meter, and then even the table gets completely wet? Then I just take the box and I put it over something higher, okay, over a shelf or something. And the time that they call it a flood and they really evacuate is when the small children cannot hold it anymore. So it's something like a meter and a half, something like this. While for me, if you ask me, when I get to my apartment, if I ever get to my apartment, and I'll only have 1 centimeter of water throughout the apartment, I will completely call it like a total loss. We'll go find another place to live in and something like that. And for them, a change in like 10, 20, 30 centimeters might not be a very big deal. And what we did with that from that year, like this was a year and a half ago, or maybe a year ago, we've changed the way that we issue the alert. So we internally know for every pixel what would be the water level. And what we initially chose to do is to generate risk polygons. So you would have like the low flood risk, the medium flood risk, and the high flood risk, like you can see here with the dark red and light red and something in the middle. What we are doing today is we are more focused on telling individual or locations what is going to be the extent of the flood in their area. So some person could get an alert for water will rise by 20 centimeters in the next 2 days. while his friend from the next village will get water will rise by 40 centimeters in your area by the next, I don't know, 12 hours. So internally, we are able to like, we do have this information, and it's, again, pretty reliable. It mainly depends on the DEMs themselves. So, and I don't really want to get into the details of why DEMs can be not really reliable, because that's a completely different story of how do we deal with elevation maps. But assuming the DEMs are either corrected or were correct to begin with, then we can provide pretty accurate to the maybe 10 centimeter difference water level.
And that's it. That actually brings me to the other question. All the maps that you're using for this purpose, what data are you using? Are you using actual data from satellites? Are you using data from maps and agencies?
So
I mean,
for the DMs or for the precipitation, for example, or things like that?
I'm not actually sure what's DEMs.
Okay.
But
yeah, sure, go ahead.
No, I'm just saying. In the end, you're following some sort of a geographical data, and sometimes when you look at the data that is in agencies, it can be outdated. For example, I've seen several mountains flattened in order to build neighborhoods, and suddenly the whole topology changes.
Okay, so first, maybe for again, I'm not sure how well the others are familiar with the DMs or things like that. So,
Zach, first in this call, we have some people who are from exactly the hydrology field. So I would say go ahead. Just one remark, because we had an interesting comment on YouTube. Partha, I think it's Indian name, comments here that knee level water is a commonplace in rainy season in India, for those of us who are less from this area.
Yep. So that's exactly what this gentleman told me. Like when I was looking and telling him, like, whoa, it's completely flooded because the water just reached my knees, and he was like, that's nothing. Like that happens like all the time. We don't really do anything when it's only knee level. And then we understood, and I'll get back to the DM shortly. Then we basically understood that what we need to focus on is not to tell them it's going to be flooded today when our definition of a flood is like 10 centimeters. What we need to do is to aim for telling them it's going to be a rise, or there is going to be a rise of 1 meter in 48 hours. And then they can actually do something, because if now it's knee level, if you add a meter to that, then that's life danger flood. And if they know that it's going to happen in 48 hours, maybe they can do something, okay? Or be more prepared. So I'll get back to the DMs, although I really don't want to take a lot of time on the hydraulic part. It's fascinating, but that can easily fill a full hour. DM is the data elevation maps, and basically it's a grid of longitude, latitude, and the value is the actual altitude of the pixel. That's in general. There are some open source DEMs. They are very coarse, and we cannot really use them for reliable fluid dynamics modeling. So what we do in Google is that, well, we obviously have other groups that needs DEM, okay, that need very accurate DEMs for other purposes, like Google Maps, for example, and others. And they are able to generate for every place on Earth using a stack of cheap visual images taken from open satellites. Like you don't need to do anything. Just buy some stock of visual images of the area that you want to model, and using some pretty nice algorithms, they can pinpoint the DEM and generate much more fine-grained DEM. It's actually very, very interesting. And if you can, like, I don't know, I can help you maybe try to get them to present this, because it's really, really nice. But let's assume for this purpose that we have DEMs in a very fine resolution.
Okay, excellent. Appreciate the answer.
Sure.
What's the resolution?
I'm not sure if I'm allowed to say. I really don't know. I can tell you that the open source ones are around, I think, 100 meters per pixel or something like this. And that's not enough. 100 meters per pixel will will give us polygons that basically cover the whole area or something like that. Okay, let's move on to the hydrologic model. So if you said, Peter, that many people here know hydrology, maybe I'll just skip those slides or at least go pretty quick on them. What I did here is I just added a few slides on some terms that I'm going to use in this talk because most of the time computer science people don't really know anything about hydrology, and I didn't know anything about hydrology 2 or 3 years ago. So I'll only cover the basic terms, and these are things that we will use during this presentation. So first of all, there are two quantities that we normally measure. There is discharge, which is the amount of water that is flowing through the river at a specific time. So normally it would be a volume per some time range, could be cubic meter per second or cubic feet per second or whatever. And there is the water level, which is the other quantity, much easier to measure, okay? Maybe I'll mention later, there is a problem with measuring discharge, specifically in very wide rivers. And water level is, as you could guess, just the level of the water measured by meters. It could be with respect to some reference point that we define as 0, and it could be like above sea level sometimes. And that basically tells us how high the water get. Measuring water level is very easy. It could be with a radar, or it could be with someone going with a stick, with a ruler, and just put it in the river and reads the measurement. That happens a lot. And basically measuring both of these quantities is what's done in what we call a gauge. A gauge is, for example, here, this red point, and a gauge is a device. It's normally an actual building, a small building in the river, because it has a lot of sensors in it. Sometimes it's a manual gauge, and that's most of the times what we deal with. So a manual gauge would be, just as you can imagine, someone going to the river once an hour and just put the ruler and get the reading. And that's basically the reason why we work with water level, because that's what's available in the large rivers in India that we deal with. Discharge is much more sophisticated to measure, mainly because you cannot really accumulate the volume of water that run through a river that, for example, the Brahmaputra River in India is huge. So in its downstream stations, we talk about a river that can get to 20 kilometers wide, okay? So that's an enormous amount of water, and that's something that you cannot really actually measure. So the way to measure discharge is by some proxy and some approximations, and you can put some device in some places on the cross section and in some depth, and then you can try to estimate the discharge. But it won't be very accurate. Water level is much more accurate, but water level has the problem of not being an additive quantity. So you cannot really say that if I take the river that I just drawn over here, then if this is a sub-river A and this is sub-river B, if I had a discharge of 100 cubic meter per second here and another 150 here, then I could expect something around 250 here. Okay, you could maybe take evaporation out or something like that, but normally it would be something that is additive, and water level is completely not like that. So they are, if it's above sea level, then it's just not the same reference point. And even if you do use a reference point, it really depends on what's called the rating curve of the gauge. I'm not really going to discuss this, but the rating curve is basically how much the discharge affect the water level. So if your river is very wide, then you'll have to pour in a lot of discharge in order to raise the water level by 1 centimeter. And if your river is very narrow or steep, then every 100 cubic meter will probably result in a much more significant raise in water level. But for now, I think what's important to understand is what is discharge, what is water level, and that the gauge is the device that measures them. And we have gauges across the rivers. Every maybe few dozens kilometers would be an approximation for that. Okay, so a gauge is something that we have, at least in the Brahmaputra and the Ganges rivers, we have maybe 100 gauges in these areas, if I'm not mistaken. Another thing that is important is what is a basin or a watershed. So this is basically the area that drains to a specific point. if you look here, that's the same river that we have had before. I now added some mountains over here. And now you can, now what I'm basically telling you in this chart is that if you look at this red dot over here, the green area, more or less, yeah, I'm not very accurate, but the green area would be something like the basin or the watershed of the red dot, because all the rain that fell inside it, like here on this rim of the mountain, will basically flow down, which is right, and then will reach that river. And the same would happen here. Some rain will flow here, some rain will flow here, but eventually they will all merge together and get to the red point. So that's the watershed of the red point. And now what we see, like here we saw the large watershed, and now what we see is that we can define a watershed for every point in the river, actually for every point in general. So we can take the large watershed and split it to sub-basins, okay? So if I only care about this sub-river, then this would be the correct, like the matching watershed. And if I'm only looking on that river, then I'll probably have the watershed somewhere around here, okay? And then the large one will have both of them plus some leftovers. So basically, that's all I'm going to cover about hydrology. If we get to any term that I'm mentioning and you're not really sure what it is, then just, again, feel free to stop me and ask. And after this crash course in hydrology, I'm going to discuss modeling in India, which is not HydroNets, okay? Just regular modeling in India, what we did initially, what we're actually doing today. And then we'll see the problems with it and why, in order to expand to all India and maybe to other countries, we need something that is stronger and can encapsulate more information. So first, when I say India, there are a lot of gauges in India. That's what you can see with the green markers over here. We are currently, for hydrologic modeling, we are currently focusing on the red and the blue areas. That's the Ganges over here in red. Ganges basically flows like that. And then you have many sub-rivers, okay, that gets into the main river, like here. So these basically, more or less, maybe I've missed a few, but basically these are the relevant gauges for the Ganges River. And these are the relevant gauges for the Brahmaputra River, which now I see that I may have a mistake with these ones. These could flow here into the Ganges and not here into the Brahmaputra. It doesn't really make a lot of difference for now. An important thing to say is just notice how wide the river is. This is the end of the Brahmaputra here in Bangladesh. And when it's not covered with markers, you can actually see that the river itself is pretty wide. So this is the area that I talked about when I mentioned that the river can get to 20 kilometers wide. That's exactly in these areas, where if you go upstream, you will see it get smaller and smaller to maybe 500 meters, maybe even 100 meters or something like that. Anyway, these are huge and enormous rivers. So I've mentioned, actually, we see it here in the previous slide. We said we have a lot of gauges. Let's just take the Brahmaputra because that's the example that we have in the next slide. So we have a lot of gauges on the Brahmaputra. And what you could immediately ask, and that would be a pretty perfect question, is let's look on the correlation between gauges. Okay, so if we have Dubri is the most downstream gauge of the Brahmaputra before you enter Bangladesh, which is just a different country, so we don't have its data. So Dubri is the most downstream, and then Guwahati is like 170 kilometers upstream. And what you can see is that there is a clear correlation. There is a shift and a very clear correlation between the readings of the water level from Guwahati to Dubri, basically. Okay, it's a pretty causal connection. So water that were measured in Guwahati will eventually, after something like, if I'm taking the peak over here, maybe that's July 8th, and that would be July 9 or a bit later. So you have like 36 hours, something like this, that takes the water to reach from Guwahati to Dubri, and you can clearly see it in the charts here. And then you could ask, okay, so if we can find these correlations between gauges, why not trying to just use it for prediction? So what we did is we trained a multivariate linear regression, a simple one, no tricks applied. and we are trying to predict debris using information coming from its sources, from its upstreams here. And you get something like that. And as you can see, that's actually pretty nice. Okay, you can see the charts. Well, I'm not really going to discuss the actual metrics that we want and what is the score of this model, but you can see for the untrained eye, it looks okay. Okay, it looks like we can make a nice prediction using just debris and maybe its few direct upstreams, and that's great. But that misses on something pretty important. The gauge-to-gauge prediction only works when you have upstream gauges, or when you have large and reliable upstream gauges, which is correct for debris and for Guwahati and for other stations that are downstream. But then if you try to model the upstream, actually, if you look on the river as maybe a graph or a tree, then if you try to get to the leaves of the tree, they don't even have an upstream. So obviously you cannot really do a gauge-to-gauge prediction with them. And even if they have an upstream, they maybe only have one upstream, which is a very small station. It's a very noisy station, and then we actually don't really get very good results. So what we started in production for this year was mostly the gauge-to-gauge modeling for the large stations. And then during the year, during the monsoon season, when I say monsoon season in India, it's actually just ended. So it's normally between June to end of October, end of November, maybe something like that. So we are just at the end of the 2020 monsoon season in India. And what we're trying to do now is basically to be able to expand our models to more gauges that are not only downstreams and not only debris, which is a fairly easy gauge to forecast. And for that, we chose to take advantage of the prior knowledge that we have about the river. And we basically want to leverage the river structure. So what you see here is a zoom-in map for the East Brahmaputra. So maybe you do not, maybe you can't read it, but here, this is debris. That's, as I said, the last station, the downstream, the most downstream station of the Brahmaputra River. And this is the border with Bangladesh, okay? So these stations over here, Guwahati, by the way, is this one. These stations over here are fairly large and fairly easy to predict. But then we ask the questions of what happens if I want to predict something over here, or maybe something over here, more into the mountains, where I don't have a lot of upstreams. And even if I do, the data is very, very volatile and it's very hard to predict.
Tzach, there is a remark a couple of minutes ago by Sopan from the chat. He mentioned that the Brahmaputra catchment seems incomplete. There's quite a big Chinese component as well.
Oh, yeah, he's definitely right. Mm-hmm. I don't think I have a map, a full map. Maybe we can go to Google. Let's go to Google Maps. I think we have some time in stock. Yeah, it's actually, it amazed me as well. If you look on the watershed of the Brahmaputra, give me that now or something.
Hi, this is Sopan here. Maybe if I can join in. I think the Brahmaputra gets quite big even by the time it enters India. Yep. And so I mean, I did read your this paper yesterday. Mm-hmm. And one of the questions that I had was that, is it like, what effect does it have if you do not consider all that upstream part, which is contributing to your river as well? You have only considered the Indian part of Brahmaputra in that. And does that affect your analysis?
I'll answer that, but maybe actually I'll answer that shortly now, but maybe we'll get into more details later after I show the actual model, because we can take into consideration the precipitation over the Chinese area. What you actually mentioned is that this is the Brahmaputra River for the other people in the audience. And what you basically mentioned is that, and that's correct, this part over here is also a part of the watershed of the Brahmaputra. So if you look at debris, basically water that falls here will eventually, after a lot of time, will eventually flow in the river and eventually will reach debris. So it should have been an input for the model, and you correctly asked, like, if you only have the gauges inside India, then you don't know what's going on here and you cannot take it as an input. And that's right. That's a problem. We would love to have those gauges as well, if they actually have gauges there. I'm not sure. But what we can do is first we can use some classical hydrological modeling from rainfall to runoff. Okay, so I do know, like I can get precipitation images for that area as well, and then I can try to run hydrological models and get some prediction of the discharge, like even here when the river actually enters India. The second thing that I can do is that I can maybe skip this part over here. Okay, so even if I say that, okay, I can't model it, I don't know what exactly is going on, here I do have some water level measurements, so some actual water level measurements, and I can just skip the first, let's say, 24 hours of water flow. So that will probably bring me to somewhere around here. And then from here, I already have the 24 hours back information that I need. I hope I made it clear. I'm not sure if...
Yeah, that's fine. Thank you.
Okay, perfect. Again, we can get back to this after we get to the model, because then it's probably easier to explain. Okay, so I mentioned that we want to leverage the structure of the river, and that's basically what we can see here. And if I zoom in a little bit more, then you can see that I don't think this slide needs a lot of explanation, but what we do here is that we take the gauges locations, we know where the river actually flows, like who's connected to who, and then we can just build a regular graph. It will be a directed graph, and basically rivers do not separate, they only merge together if you look at the high level. So what we can say is that we have like a DAG that's basically an inverse tree, okay, something like that. Okay, depends on how you connect the edges. But that's a fairly technical process. We can easily do it for every river, and then we manually maybe correct it. And what we have here is the structure of the whole river. And then just before I get into HydroNets, we ask ourselves, is it even useful? Is it even beneficial to use the structure of the river for prediction? So what we did is we took debris as our station, and we tried to train a linear model. We currently don't do anything more sophisticated than linear. We'll get in the end of this talk to some more sophisticated models. And we took debris and we tried to model it using a tree of depth 0, meaning features that only come from debris itself. So basically I'm taking past readings from debris and I'm trying to predict debris in 48 hours from today. That's a very basic gauge-to-gauge modeling, because it's basically a gauge modeling. I'm not even having other gauges. And then you get some baseline, some reference point of what is the performance of a linear model when you only feed it with debris past readings. Then what we could do is we could add, like we have here, well, let's say this is debris, so we can add debris and its direct children, okay? So then we get, like, we can see an improvement, which is good, which can give us some hint that there is some information in the descendants that we want to leverage. When we add the grandchildren, we see another slight improvement, but then happens something that we can probably all understand as overfitting. So the model is a linear model, and when I keep adding more and more gauges, I keep adding more and more historical data. That means that I have a lot of inputs. Since it's a linear model, the number of weights is basically the number of inputs. And I just don't have enough examples to support this. So what happens here is that the test performance drops to negative R squared. It's not really R squared, but I'm not going to get into the difference.
You also have correlation between the variables here. It's not only that you add on variables, but the ones that are linearly dependent.
Yep. I hope not to get into that, but the correlation between the variables actually cause and still causing us a lot of problems. Even today, when we don't use a linear model and when we try to optimize with different models, this correlation makes it very hard to converge to a good place. There are some other ways to try to deal with it, but I don't think we have enough time to deal with that today. But basically, I just wanted to have this chart in mind. So in a few slides, when I'll see the solution for it, we can see the improvement. What we basically say here is that the good part is that we see that there is some information in the descendants, and that actually makes perfect sense, because the descendants can give us some glimpse into the future, basically because this water will eventually flow into us. So it's a good thing to use the descendants, but probably not naively as just concatenate everything and try to learn a massive regression. What we did to solve this and to be able to leverage information from more gauges in the graph is we developed something that we call HydroNets. That's a general architecture. And into this architecture, we can plug in different models that will do different tasks. And I'll touch this in a few slides. Before, maybe some guiding principles that we had when we thought about it. Then first, we obviously recognize the causality between the basins. So if we just concatenate all inputs and try to run a simple regression, we basically say that we allow connections from all the gauges and all the readings to the output, and maybe that's not really correct, because that's actually what's causing us to get to this overfitting. But what we are saying is that there is causality between the basins, and if NumSci has to get or to rely on data from Motipur, then Dolabazar, and I'm sorry if I'm not pronouncing it right, it's correct that it relies on data from Motipur, but it could maybe only rely on data from NumSci, because NumSci should process the data from Motipur and then only output something that is already composed. Or so that's something that we wanted to have in mind. The second thing is that we think, or we believe, that some of the modeling of the hydrological modeling can be shared between all the basins. So although they are different, although the water level are different, although their behavior is different, because this one could be in a mountain and the other one could be in a very flat area, or the soil type could be different and everything, we still believe that some part of the modeling should be shared. And that will allow us to use stronger models in order to model that. Having said that, obviously, the other part of the modeling has to be basin specific. So we'll see in a minute how we did that. And as a nice property, we wanted, we thought about it, that data should flow in the network as water flow in the river, and that would help us accomplish basically the first task. So I'm going to go into a single node in HydroNets, and then we'll see the whole graph, because it's much easier to explain a single node. So a single node in HydroNets basically corresponds with a single basin. So for now, forget about the whole graph. Let's just focus on a node. This unit, this layer needs to predict. You can see it here. You can see it. Whoa. Yeah, sorry. Okay, you can see it here. So this is the node, and what it has to predict is the label for this basin. And we are normally trained with water level as label, but it could also be discharge, okay? But the node is also responsible, if you look at this arrow that goes out, node is also responsible for generating what we call its temporal embeddings. So we define the state of the river by some vector of size h. It's normally 8, but we're playing with other numbers as well. And this vector should encapsulate the state of the river, whether it's a discharge flow over the river, whether it's a underground flow, whether it's just, I don't know, a humidity or maybe some other condition that we're not really sure what it is. It could also be a snow accumulating in some areas. Everything that is important for the downstream node to take a better decision or to try to predict itself in a better way should be encoded in these embeddings. And that's the responsibility of every basin to generate its own temporal embeddings. So that would be a vector of size h over this axis, and t is the temporal axis. So let's look on how does the vector, how does the basin, do that. this is actually where the shared part of the modeling comes in. So the shared model is more like again, for all the hydrologists in the audience. So that's basically the rainfall runoff modeling, or at least was inspired by the rainfall runoff modeling. And what we do here is we have the inputs, such as maybe past readings of water levels. It could be precipitation images. It could be precipitation values. It could be temperature, humidity, solar radiation, all the classical features that we can use in a hydrological model. And these all are features that are calculated for this basin. So, okay, just remember this node reflects a single basin in the chart, in the graph. And these are the calculated features for this basin. But what it also receives, it receives the temporal embeddings over here. The downstream node arrow basically gets into here, okay, in the downstream node. So every node also receives the temporal embeddings of all its direct children, but only direct children. And that's basically are the boxes that we can see here with source 1, source 2, until source n. Let's assume that this node has 3 children, three sources. Then it has a model, a submodel that's called, we call it the combiner, which basically accounts for the relative importance of the sources. So it could be that one source is a huge river, maybe the Brahmaputra, and one source is just a small creek that joins. And the combiner needs to take that into account. And also, theoretically, the distance from the basin to each one of the children. Okay, so it could be that like I have a basin over here, I have a gauge over here, and it has 2 children. One of them is very, very close to the actual gauge, to my gauge, let's say maybe 1 hour apart, 1 hour in terms of water flow. And maybe the other is very far away, so it takes the water like 24 hours to reach me. The combiner needs to align them together, okay, to learn this alignment and actually combine them properly. The combiner is a per basin model, basically because the number of children for each basin is different. So we cannot really train a single combiner for everything, and we have to have this as a per basin or per watershed model. But the output of the combiner is the same for everyone. So the combiner will always output a vector of t over h. Okay, and h here will be the combined embedded vector. That actually what causes the shared model to be shared, or to be able to be shared, because all the inputs here are the same, or at least of the same shapes. Okay, and then this is the shared model. It generates the temporal embeddings for this node. We do have some other mechanisms which I'm not really, I won't really get into, but you could add attention here and some other nice stuff. They tend to help, but it's not the crucial part of the model. And the temporal embeddings will, as I said before, go to the downstream node and will actually be fed here to the downstream node. But they also go to the predictor, which actually translates from the embedded vectors to the actual label that we are trained on. And again, this is basin specific, mainly because, for example, if we work with the water level, then the rating curve is a property of the basin or of the gauge. And that's something that is different from basin to basin. And we generally want the predictor to be able to learn that. Okay.
A couple of questions here. Where are the trained weights? Where do they reside? So of course in the label predictor, but where else?
Okay, so the label predictor has its own weights. The shared model has its own weights. You know what? Maybe I'll just mention what are these models. I plan to do it in the next slide or maybe in 2 more, but I'll do it now just so we can actually talk about the weights. If you recall the chart from before with the overfitting problem, then that chart was with a regular linear model. Okay, so we didn't do any trick there, and that's not a very strong model to begin with, but we used the linear model because we wanted to have some baseline that we can actually compare to. So then we could claim that the improved performance that we are going to see in a few slides actually comes only from using the structure of the river and not from using more sophisticated models, which is what we actually do in reality. So HydroNets doesn't really care what is the combiner, what is the shared, and what is the predictor model. it gives you like placeholders to put whatever models you want. And like the examples that I'm going to show in the next slide are basically what we call the linear HydroNets. So it's the HydroNets architecture. You build the whole graph, or you build nodes like I'm currently describing, but the models that you use inside are linear regressors. Okay, so the shared model will basically just flatten out all the features and just predict a vector of size h, let's say 8. And the predictor will be a linear, just a simple dense layer, so a simple dense layer with a linear activation from a vector of size h to 1 to the label. And the combiner, again, will learn some transformation from, let's say we have 3 children, so from 3 over h to h, okay? We'll just combine them together. These are very, very naive and definitely not the best models to use, okay? And I'll touch that in the last slides. I'll touch what can we do beyond the linear models. I'll just mention that the reason why we use the linear HydroNets in these experiments and in the paper, for those of you who read it, is basically because we wanted this accurate comparison to the non-structured linear model. So what we showed there is that the structure helps, and what we actually do is we use the fact that structure helps, but then we just replace these models with LSTMs and convolutional networks and other things.
Another question about this here, while we're on this slide, just to understand. So the structure of the river is basically the way you build the model, but the quality of the ground, let's say, and the length between one point to the next point, where does this reside? Is it the input on the left side? Is it somewhere else?
Okay, perfect. The soil type, for example, whether it's rocky or sandy or any other kinds of soil types, that obviously has a lot of importance over how water will flow over the ground. And this would be here. This would be a feature of the basin. So imagine I can pre-calculate maybe the percentage of rocky ground in the basin for this gauge. And that would be a numeric feature in the model. Maybe it could be even a map. If I really want to be more sophisticated, I don't think we need a map at this moment. Like we have more crucial problems to deal with before we start, looking at maps of soil types. But these kind of features will be here. So precipitation that fell over the basin would be an X, and the soil type would probably be here as Z. X and Z are like a minor difference of dynamic and static features. Nothing too crucial. And the other thing that you said about the distance between the basins, that's basically something we do not provide the model with actual data for. So I don't tell the model for every basin, you have 3 children. Like I do build a graph so it knows that it has 3 children, but I don't tell it something like the child number 1 is like 100 kilometers apart, and child number 2 is only 10 kilometers from you, and child number 3 is 500 kilometers. I do expect the combiner to learn this. And maybe I'll touch that when we talk about the convolutional combiner.
So you actually don't have any relation between the child and the parent, aside from that they exist as child and parent. Let's say difference in height, difference in distance, difference in whatever else. Let's say if there's a dam in the middle or a small dam that is blocking water flow, you don't have any of this information embedded. Right. You expect the combiner to learn this by itself.
I expect the combiner to learn the temporal difference between the gauges. So if there is a distance between them and that causes some temporal distance, then yes, I definitely expect the combiner to just learn it. As for dams, that's another great question. We currently, knowingly, we do not handle dams. So if there is a dam somewhere in the middle, we will probably not use HydroNets in that area, because we don't have the mechanism of saying that I have a gauge and a gauge, but here in between I have some dam. So a dam just completely changed this whole behavior, because there is someone with a switch and he can decide if he wants to open the dam or close the dam, and that's not something that we can easily model. However, we do work on solutions for that as well, but it's very preliminary. What you said about different scales for the water level, so maybe debris is something around 25 to 30 meters above ground level, above sea level, and maybe in the mountains you see readings of 150 to 160 meters. That's great. We do expect the embedded vector to be generic and to work for all the gauges, because again, this should reflect something more similar to the discharge and not the water level. And then the predictor will be the one to actually translate back into the water level that like for every basin separately, and then it can actually put it in the right scale. I think I'll move on to the next slide, and then we'll do some stop for questions, maybe before we discuss the non-linear HydroNets. Okay, so that's a fairly self-explanatory slide. After we discussed a lot about each and every one of the nodes themselves, then what we can do is we can take the whole region, and as I said before, we've built a graph from this region, and then we just build a node for every node in the graph, and we connect the edges from every temporal embedded vector into the downstream node, and we basically build the TensorFlow network similarly to how the graph looks like and to how the river flows. That's how we basically get the whole model, and the model predicts all the labels at once. So at every iteration, at every example, we basically predict the water level for all the gauges at once, and we also generate loss for all the gauges at once, which helps us a bit with conversions. Okay, so as I promised, I get back to the overfitting chart from before, and the blue one was what we were used to see when we actually overwhelm the linear model with too many inputs. It just starts to overfit. And what we see when we do the same experiment with HydroNets is that it doesn't overfit. Okay, it only gets better and better slightly. Here you can say that it's fairly the same performance, but at least it doesn't overfit, which allows us to leverage information from many gauges without having the fear of, oh my God, this chart or this tree is too high, and I probably need to trim it, and I probably need to train a lot of different models. And that actually allows us to train all the basins together. So the shared model can actually be pretty strong. Again, I will just mention that these results are with the linear HydroNets, okay? Because that's not really the HydroNets that we are playing with going forward. Okay, actually, I won't spend a lot of time here. We did an experiment on two regions that we manually constructed the graphs for. So when I say Ganges, it's not really the whole Ganges. It's I think only the Yamuna River, which is only just a small sub-river of the Ganges. In our region, it has something around 20, 25 basins or sub-basins. And the Brahmaputra is the area which we've seen before that has around 40 to 45 gauges. And you can see the full results in the paper, so I'm not really going to get into numbers, but basically what we saw is some clear improvement over the linear baseline, which was a good sign that when we constrain the model and when we only allow it to use the direct children and we force them to propagate the information from the more upstream descendants, we actually get better results, okay, than just using a linear model for all. And that basically led us to try to improve HydroNets. So we've designed HydroNets to be a general architecture. So we are not really doing anything linear inside HydroNets. HydroNets only builds the graph, builds the network, it connects all the models together, it controls the inputs and what goes where. It could maybe force some attention mechanisms or some others, but it doesn't care what is the shared model and what is the predictor model and what is the combiner model. So with the linear HydroNets that I said before, we used linear regressors for all of these. And what I'm going to mention now is just some ideas that we have. Some are more actual experiments and some are more ideas for using different models for different parts of HydroNets. Maybe before that, we can make a stop for questions if there are on the linear part of HydroNets or on how HydroNets is built.
So Sopan had a question before.
Hi, if I can ask them, I can. Yeah, hi Zach. Yeah, so the question I had was that this states combiner model, that step that you have where you are combining the, let's say, the outputs from the upstream nodes. And I think in one of your previous slides, you mentioned that you assign them relative importance. And the question I had was that whether this relative importance is just simply based on their relative drainage areas, or do you let the machine learning model decide that? And a kind of related question to that, when you showed the results of how your hydronets, linear hydronets, the deeper you go, you kind of reach an asymptote, like it flattens out. So does that mean that you can have like a kind of a cutoff point after, let's say, you go maybe 4 or 5 upstream nodes deep?
Okay. So first of all, about the combiner, yes, we do expect it to learn by itself the difference between gauges. Okay, so if it has like a very close by gauge, it should learn by itself without us providing it with the basin areas or something like that. What is the importance of each and every one of the children to the drain? And we hope and we get some nice results that it can actually do it only by looking at the data itself, only by looking at examples. And we don't need to force it to provide some more strict or direct features in order to do that. However, we do think about adding more, like it's possible to add the drain area and the distance between gauges as features to the combiner model, maybe to help it get the right decision. Our current approach is to try to do it in the machine learning way. So just let it look at data and decide what is the convolutional filter it needs to use.
Yeah, okay, thank you.
No problem. Any other question?
Is the combiner also able to tackle missing data?
Perfect question. We just had a 1 hour discussion about missing data in our production models today. We currently do not directly deal with missing data. What we do on train is every time we have missing data, but in historical data, it's less common that you'll see missing data because normally maybe it's missing in real time, but then they will correct it later. So in historical data, we normally have the information and we can train. If we have missing data in the training set, we just drop the whole example. But your question is perfect for the real time. So when we actually run the model, a lot of times we have missing data because station is down or the file transfer was corrupted or whatever reason, we just don't have the information. And we just had a discussion today about how do we want to mitigate that. We can either use the fact that that we don't need to get to the whole tree, that we kind of saw an asymptote after a depth of maybe 3 or 4, something like that. So if we know that and we have missing data in an upstream that is like maybe a depth 4, then it shouldn't affect us because we could just maybe trim the tree or ignore this data or do something like that. That's one solution, and we would like to do it as automatically as we can. So not building a lot of models, but having the model be able to trim whatever it needs. We still need to see how exactly we want to do it. Another thing which I'm kind of in favor of is to just simulate these during training. So just augment the data and take the perfect data that we have in training and just feed it with override it with nonce in specific places. Maybe try to simulate what happens to us in real time. So normally the things that we normally see in real time would be that a specific station would have like a gap of 12 hours without data or something like that. So we can just augment the data and create this even in the training set, and then probably if we add another Boolean feature of is missing data or something like that, the model might be able to ignore it itself. These are still just ideas, and we actually need to experiment with this.
Okay. Thanks.
Sure. Okay, so let's move on to the last slides. Basically, let's start with the shared model, because the shared model in the linear HydroNets is, again, flattened all the inputs and just uses a linear regression, and that's obviously not the best hydrological model. We know, and we have the link here to this paper of Freddie Kreitzert that shows us that LSTMs are much, much better at hydrologic modeling than SAC SMA, I think it's called, many actual hydrologic modeling that are calibrated per gauge. Freddie was able to show that if he just trains an LSTM for all gauges together, he gets better results than the per gauge calibrated SAC SMA models, which is pretty amazing. And then for us, the easiest choice for the architecture for the shared model was, yes, let's just plug an LSTM in there. We have temporal features, we have static features, so we can just duplicate them over the temporal axis. And we have the combined embedded vectors, which are also temporal features, so we can just stack everything together, feed it into an LSTM, and just see what happens. And that performs pretty well. We've started looking at this quite lately, and what we are trying to do now is to actually use LSTM in a smarter way and solve some of the problems that we saw in order to have a stronger and a solid main engine. So the LSTM will probably going to be the main engine of HydroNets that is going to do the rainfall runoff modeling. And we obviously need to add more features. So in our experiments, we only used precipitation was there, and also the past water levels, but we didn't use temperature, soil moisture, and all the others, just because we didn't want to add more complexity, more unneeded complexity. Again, to remind you, in this paper and in these experiments, our only goal was to show that the structure can help us. And if we were to convince that structure helps, then we can go and try to develop HydroNets into a stronger model. So we did that only with water level and precipitation. And what we are planning to do now is to use a lot of other features, as many as we can get. Another interesting problem, and I don't really have a lot of time to get into, so I'll just mention the problem, is that we probably want different features to have different time resolutions and maybe different ranges. So I could say something like, I want to look at water level from the past 3 days in an hourly basis, but I want to look on precipitation from the last 4 months in daily resolution. Okay, so these two are different, and we probably need to split the LSTM to 2 parts, maybe the longer history, then the shorter history, and chain them together. If I move on to the combiner, so the linear combiner is obviously very, very dummy and cannot take into account anything that is something like the distance between the gauges. So it can only take into account the importance of the children. But it's only something like children number 1 is more important than children number 2. So the weights of children number 1 will be higher, and then the weighted average, which is basically what it does, will just put more importance on that child as well. And what we currently have is a temporal combiner, which is basically, again, I can't get into more details just because we don't have a lot of time, but you can basically think about it like a convolutional neural network, where we learn a convolution kernel per child, and this kernel is over the time axis, and this kernel is then applied for the whole embedded vector. So we expect, maybe I can draw something here, I'm not sure. Wait a second. Yeah, okay, I'm not sure if I can draw here. Maybe I won't even try. But anyway, you can just imagine a kernel that looks like, that is maybe something like a gamma distribution PDF. So you have like a quick raise where the water actually came in and actually affected the downstream node. And then you have a quick increase, and then some long tail of how relative the vectors from the past, I don't know, 24 hours and 48 hours are for t equals 0. That is what we try to predict at the moment.
Is it a one-dimensional kernel with, let's t kernels per child, or?
It will be Yeah, it will be. So let's imagine that T is something like a week. Okay, so let's imagine that we have a week of data, and we define the kernel to be 24 hours. So it will be like a one-dimensional 24 hours kernel just moving over this week. The only thing is that this kernel is applied for the whole embedded vector. Okay, so we just multiply the whole vector, which can be at size 8 or something like this, with the same kernel.
So the length of that one dimension is n times h.
Yes, but that's a debate that we have, whether we want to allow the kernel to mix channels in the embedded vector, or we actually want to force it to be only the weighted average, only the kernel, like the temporal kernel, and then we will keep the vector as it is. We still haven't got to a conclusion of which one is better. We're trying both.
Okay.
And the last slide here is how can we make the predictor better? So the predictor, again, just to remind you, has to translate from the embedded vector into the label itself. And in India, we currently work with water level as the label, while since we've built the graph, or the network computational graph, we've built it like the river, we kind of expect these hidden embeddings to behave similarly to discharge, which is something that is additive, that you can just take the discharge from A and from B and pour it together and add it together, and this will reflect, or this will be the discharge of the downstream gauge. But then at the end, we still need to predict the water level. So in hydrology, there is something called the rating curve that's similar to what you can see here. That basically translates from the discharge over the x-axis to the water level, and that's normally a monotonic increasing function. What we are currently playing with is just having some piecewise linear layer, a layer that basically splits the range into a few beans and then learns just a slope, a positive slope for every bean that should simulate the rating curve, at least as we know of, from the hydrological knowledge that we have. And then we will allow the predictor to apply some learned rating curve over the embedded vector, and then maybe just some regression to collapse everything to a single value. We see nice results with the synthetic data. We still have some convergence problems with real data, but again, it will probably be solved. My last slide is actually, well, first of all, thank you all for joining. I just wanted to maybe recap what we went over. So first, the flood forecasting warning system, that's something that we already have live for, that's the 3rd year, but this year we actually covered almost all of India, and we had a really great impact on users. So like millions of users got the alerts and opened them and got notified, which is really great. We do plan to increase both coverage and, of course, the horizon and the accuracy for the next season, which is in about 6 months. I've touched on HydroNets. I basically presented the basic HydroNets that we have, and that's a generic architecture that we can then plug in multiple models. It basically builds the river-like network, and then it allows you to plug and play different models for different parts of the hydrological modeling. If you have any other questions other than what we can do now, feel free to reach out either to me or to Asher. You have both emails there, and I'll send them to Peter so he can put it somewhere in the comments. GCO/floods is what I find a very nice video. It's a 5-minute video called When Rivers Rise. And When Rivers Rise is a video made by the PR department of Google about this project. It's really nice, inspiring. You can get to see things, but again, that's a PR, that's not a technical video. And the paper itself, so Peter, I guess we can share a link, we can share the paper, we can share.
Yeah, it's already shared in the event, and this YouTube recording, it's everywhere. Yeah.
Okay, so basically that's it. And I think we have like maybe less than 10 minutes, but I can take like as many questions as we can make, and the rest will be in Reddit, emails, whatever you want.
I have a question, actually. I'm curious. I don't remember if you mentioned it or not. In production now, are you using the linear model, like the sophisticated linear model, or do you use the convolution already?
So as with all production systems, normally it takes like a year or two for the research to actually get to production. So for production gauges this year, we used a variation over the linear model. So I presented something very simplistic, just concatenate all the upstreams and then do some linear regression. We have something that is not very far away from that, but with some tricks and things that we did to make it like perform better. But yes, I think the most important thing is that in production today, what we have is a specific model per gauge. So every time we want to launch a new gauge, we need to decide on its upstreams, we need to train a new model, we need to evaluate this model, and then we need to deploy a new model only for this gauge. And what HydroNets provides us is maybe a reliable way to just train a huge model over, let's say, a model for the Brahmaputra River, and then you get 50 gauges at once, and hopefully the results will be even better than just training them one by one. And we have some promising experiments that shows that. So I'm optimistic.
Very nice. Any more questions? Anybody?
Yeah, I have a question. Hi, Zach. Really great talk. I really enjoyed the work that you have done. Just out of curiosity, how much improvement are you talking about when you use this long short-term memory model? Because I think like when I saw the R-square values, what you're getting from your linear models, I think you're already getting them quite good. So are you just doing too much work for a very small increment? Or are we talking some really big jumps over here now?
Okay, so I think you referred to the R-square that I showed for the debris station, which this is a station that we use for the overfitting to show the overfitting in the linear models. And then you actually saw R-squared of 0.9 or something like that. And in debris, it's not very uncommon to see R-squared of 9, maybe even 9.5 or something like that, which you can say, why even bother trying to increase that? That's pretty perfect. So I'll say two things. First of all, the regular R-squared is kind of problematic because we don't really care about our prediction while the river is low. We only care very, very much about our prediction where the river is actually above the danger level. So when it's actually a danger time for the river. And more than that, so first of all, we would like to penalize more the upper parts of the charts, and that's doable. But we also want to penalize for time lags. So even if I predicted the correct water level, but I did it 6 hours after the actual rise, that's a problem because I promised my users 48 hours in advance. And if I just missed by 6 hours and add to that the time that it takes to the measurement to get to our systems and everything, then maybe I'm now providing them with a much, much smaller horizon of maybe even less than a day. And that's something that we wanted our model to be able to train for. Okay, so to be able to train using maybe a different loss function. And the second thing, so first of all, don't get your hopes high just because we saw some 0.95. The 0.95 also could have a lot of dramatic failures that for us in real time will be a failure of the system, although the 1 season chart gets 0.95. But the second thing is that 0.9 are scores that we can only get for the downstream stations like Dubri, Guwahati, and all these. If you really want to cover the whole of India and the whole rural areas, the villages on all the sub-rivers, then you need to go to upstream stations, and upstream stations do not get 0.9. So upstream stations normally get even a negative R-squared or something around between 0 to 0.5, which is not really acceptable. And what we basically claim here is that while the gauge itself, the upstream gauge itself, maybe it's small, maybe it's not, it doesn't have a lot of data, maybe it has a lot of noisy data, and maybe it's kind of a weak in terms of trying to model this gauge specifically, because I'm training it with the rest of the tree, it actually enjoys the data that all the other gauges provide to the shared model, because again, it's the same shared model that is trained for all the gauges. So even weak stations at the leaves of the tree can still perform much better just because they were trained with the with this shared LSTM for everyone. That's something that we've seen kind of happening, and we actually pretty expect to prove it by launching a lot of production gauges in places where we couldn't launch the linear model before. Okay.
I have a couple of questions if we still have time.
Let me send a chat message and then we'll have a few more minutes. Second. Okay, sure.
So the first question I have is, I mean, it sounds like every time you add a new region or a new gauge, there is some work involved around it in plotting who is supposed to feed the data. Is there any work on trying to just try maybe some kind of a, I don't know, sparse regularization and trying to see if the machine can automatically learn which gauges to learn from? And then maybe see if there is some way to easily increase the generalizability.
Mm-hmm.
The second question is, there in the meantime, the model is on, as far as I understand, reacts only to gauge data. What about weather data? Is there any plan to implement it inside? Add also. I think I'll start from these two instead of just throwing lots out there.
Okay, so we basically, if you think about HydroNets, what we are doing is we constrain the model to learn only from its direct children. So we in a way, we are not trying to allow learning from all the gauges together and then only constrain the matrix with some L1 regularization or something like this. We build the network so the model, so the gauge can only look at the direct information from its direct children. And then what we basically expect these children is to propagate information from the upper descendants if it's important for the prediction of the downstream node. So it's kind of the other way. We chose not to allow all the connections and then try to regularize, but instead to build a network like the river and expect them to use the H, like they have eight floats to pass around. So I'm not telling the gauges what exactly they need to put in every index of H. Okay, H is not necessarily the discharge. It's some vector. It can encapsulate some data. And I expect them to play with H so they pass the right information to the descendants, and so they get, and so like all of them gets the correct prediction or a better prediction. And the second question was about precipitation or more data into the model, right?
Exactly, all the weather data.
Yeah, so weather data will be entered, like we currently only use precipitation as data, and we only use a very weak version of precipitation. So we use what's called a lump sum. We take like what the satellite sees is basically the map of clouds. Okay, so satellites can give us what was the amount of rain that fell over every pixel in the map. And then what we do is we take the basin, the shape that I showed, the polygon, and we take the basin, we crop it from the map, and then we basically average the values. So what we have is the average amount of water that fell in the basin in general. This is a very weak version of precipitation because obviously rain that fell close to the gauge is probably more important than rain that fell far away from the gauge. And that's definitely a problem when you look on very large basins. So if we look on the basin of Dubri, it covers like the whole Brahmaputra area and even China, if you actually take the actual China part, then that's a huge part. And obviously rain that fell in China will take days or weeks to get to Dubri itself. So that could be not the most accurate way to do it, but having to deal with precipitation images, for example, is just a bit more complex than we plan to do it in the future. Other types of weather data are, other types of weather data that are easier to incorporate will be incorporated as more dynamic features, as temporal features.
Got it. And I'm assuming the alignment between the effects of the different children, the temporal alignment, it all happens within, the per basin learning, or it happens within the temporal?
Definitely, because that's something that is different from basin to basin. So first of all, then your children are different from basin to basin. Okay, there are basins without children at all. There are basins with only a single child, and there are like basins with I don't know, 5 or 6 children. And even if it was the same number of children, these are obviously not the same children, so you cannot really apply anything generic here. And more importantly, what we actually expect the combiner to do is exactly this. We expect the combiner to learn whatever convolutional filter it needs for every child separately. So if a basin has 3 children, it will learn 3 separate convolutional filters, and these could be like different from basin to basin. Yeah.
Got it. Excellent. Thank you.
Thank you. Okay,
Any
Peter.
more questions? Tzach, you were gonna say, I'm sorry, I cut you off.
No, I basically was about to say that we can conclude or sum this up.
Yes. Go ahead.
Thank you for this opportunity. It was really, really great. And again, as I said, I'll be more than happy to discuss any ideas or anything. Feel free to reach out.
Mm-hmm. Thank you, Tzach, for joining in and giving this interesting talk. I think I've been trying to get you to get here for 4 months now. So I'm happy it finally happened. For everybody, I just sent a couple of minutes ago, I sent the links again where you can find the community, the newsletter, the YouTube where this is now live, and this will be, the recording will be left there and you'll have it later on. The Discord server where there is place for everybody to talk among themselves. It's an instant messenger, and of course the subreddit. We will be posting there the lecture slides, maybe today, maybe tomorrow, depends when we have them ready. And thank you for joining. The next lecture again is adversarial learning. It's covering 4 papers by the authors. All of them were published in top conferences, and after this there will be more lectures. They're just not published yet. I am always looking for more interesting speakers. So if anybody is familiar with anyone who's working on something high-end in ML, in 3D, and something to do with geography, also relevant, by the way, Tzach, this is within the scope of the community. And feel free to let me know and connect us, and we'll have them on. And I think I will say thank you and bye-bye. It's already evening now here. Again, thank you, Tzach. Thank you, everybody, for joining in.
Thanks.
Thank you very much.
Bye-bye.
Thank you.
Bye.
Thank you for a great talk.